So, good morning and welcome back. The last lecture of this chapter, we have gone over various topics related to the motor, the controller, the electronics, the software, electromagnetics, torque production, thermal consideration, many things. It leaves me a little unsatisfied. Probably it leaves you also similarly unsatisfied, because it is like taking you through a series of lectures. In one lecture I tell you how to chop onions, in another lecture I teach you how to grind masala and so on, but you still do not know how to make a meal. I would have loved to teach you ground up how to actually design and build a motor, but that is way too ambitious for this course. But as a preview of how you can apply your knowledge, I will walk you through how, even if you are not designing a totally new motor by yourself, how if you know that there is a motor with you which is working according to certain specifications, how can you make some small changes to make it perform to very different specifications. Maybe deliver much more torque, maybe become much more efficient, or maybe go at much higher speeds. So, adapting a design, as you see on the screen here, is something that you can do. To be able to actually come up with a totally new design will take some more effort, which is beyond the scope of this course, but I definitely would like you to be able to adapt a design. And then going forward in this lecture, I will cover some of the emerging trends of the future. So, shall we get on with this? One of the simplest things that we can do when we have a motor, when I say we have a motor, it may be physically a motor, we are capable of copying that motor and making another. A lot of people just take a working product, copy it, make 100 copies of it and sell it. They do not know how it works, but they copy it so faithfully that whatever they make works as well as the original. This is true not only about motors but about many products. So, if you have a motor which you are capable of replicating by copying, or if you have a design of a motor along with a document which describes how it works, but you want to change this design because it does not meet your requirements, you want slightly different requirements, then one of the simplest things you can do is that in the winding you can change the number of turns. What will be the effect of changing the number of turns? Let us look at that. So, there is a simplified sketch of the place where the winding comes, which is the stator, and the stator is made up of teeth and it is made up of back iron, and the space between two teeth is called the slot. Now, let us say that the present design has one turn. So, compared to the area available in the slot, putting one turn of wire takes up about 6% of the area. What is the name of that percentage? If I say that 6% of the available area has copper, what is the term used to describe it? It is called the fill factor. And we have already seen that practically the fill factor cannot be more than about 40%. If it is a little lesser, it is easier from manufacturing point of view. So, let us say that I want to use 36% fill factor. Beyond 36%, my manufacturing infrastructure, I cannot do it. Now, I want only one turn, but I can afford a fill factor of 36%. Then what I will do? What I will do is I will put many turns in parallel in such a way that the fill factor becomes 36%. In this picture I have put 6 turns in parallel in order to achieve 36% fill factor. Why would I do that? What is the advantage of putting 6 turns in parallel? Remember, I am putting them in parallel. When I do this, what happens is that if one turn has a resistance R, when I put 6 turns in parallel, the resistance becomes 1/6, which is R by 6. And because the resistance is 6 times smaller, my copper losses, which are normally the predominant contributor to the motor's efficiency, that loss will become lesser by 6 times, and so the efficiency of the motor will tremendously improve. This is the reason why I put 6 parallel strands. So, let us say I have a design of a motor where there is only one turn and 6 parallel strands. I am putting 6 parallel strands because I can afford in the space constraints to accommodate 6 conductors, means 6 wires. 6 conductors can be accommodated, there is enough space for 6 conductors. I need only one turn, so I put 6 conductors in parallel and I get an effective resistance of R by 6. Now, if I want to increase the number of turns to 3, earlier design was 1 turn, but now I want to increase the turns to 3. I want to know what is the impact of increasing the number of turns. When I increase the turns to 3, what you will see is that this diagram gets changed into something like this, because when I take one wire and turn it 3 times, the length of the wire increases 3-fold. So, what was a resistance of R becomes a resistance of 3R, but since I can put 6 conductors, I can afford to put 2 such strands in parallel. So, now the effective resistance is 3/2R. The consequence of this is that the new resistance is 9 times more than the old resistance. You can readily see that the resistance is proportional to the square of the number of turns, which is what I will be showing you here. The loss of the new arrangement where there are 3 turns, I am trying to compare it with the loss in the original arrangement where there is only one turn, and since loss is I squared R, I can see the ratio of I squared and I can see the ratio of R. But the interesting thing about increasing the number of turns is that when I increase the number of turns, the flux linkage becomes 3 times more. So, for 1/3 of the current I will get the same flux linkage, which means for the same torque I have to only supply 3 times less current. That is why you see that I2 by I1 is inversely proportional to N2 by N1. So, I put here as N1 by N2, but the resistance we have already seen is proportional to N2 by N1, and so since it is N2 by N1 squared. So, when I see the competing effect of reducing the current and increasing the resistance, the two effects cancel each other out and my efficiency is unchanged. So, what is the advantage of changing this, or what is the disadvantage of changing the number of turns? What happens when I increase the number of turns is that I need to supply less current for the same torque. In other words, if I supply the same current, I will get more torque. I can get a more powerful motor. By power is a wrong word, higher torque motor. I can convert the motor into a high torque motor by increasing the number of turns. But in the world, nothing comes for free. I am using the same number of conductors. Just by changing the way in which I wind, I have converted a low torque motor into a high torque motor. What is the price that I pay? There is no rupee price. I am not using more copper. Nothing I am doing. Somewhere I should lose something if I gain something. That is the law of nature. Yeah. Louder. Weight. No, the weight is same. In the earlier case there were 6 conductors, now also there are 6 conductors. Only the way they are arranged is different. Nothing has changed. The maximum speed will be lower. Because the flux linkage is greater, it means the back EMF constant is greater. So, when it reaches a lesser speed, the back EMF will match the supply voltage, it can't go faster. So, I will get a higher torque, lower speed motor by increasing the number of turns. This is the effect of increasing the number of turns. Reverse effect will be if I reduce the number of turns. But in both cases, the efficiency is not changing. Is that clear? Similarly, that is a very convenient way of quickly changing a design. Oh, I need to have a little more torque. Okay, let us increase the turns. Okay, it is a very convenient and neat thing to do. Similarly, another thing that I can do is, if I have a motor of a certain size, I can make it a little longer. What will happen if I make it longer? That is what we will see here now. So, this is a motor with a stack length of 1 inch, it has a resistance of 25 milliohms. If I make it 2 inches long, the resistance will be doubled. But again, as I was saying, the coil is now longer. If the coil is longer, it means the area of the coil is doubled, because length into width is the area. And if the area is more, flux linkage is also doubled. If the flux linkage is doubled, for the same current I will get double the torque, or for the same torque I need half the current, just like we saw in the previous example. The back EMF constant will get doubled. So, for the same torque, the current I need in the longer stack is half the current I needed in the old. But the resistance of the new stack is double, because the length is doubled. So, here again current is getting reduced, but resistance is getting increased. What will happen to the efficiency? What will happen to the loss? Will the loss be more or less? More. Why do you think it will be more? But the current is half. I squared R is the loss. The two are again conflicting with each other. What is the net result? Let us say that the new length is f times the old length. In this picture, f is 2. The new length is 2 times the old length. Loss is I squared R. The new loss by old loss is what we want to compare. So, if I do this, the current is inversely proportional to the length. L here is the length. So, if I use f as the ratio of the lengths, then I get 1 by f squared into f, which is 1 by f. So, by increasing the length, the efficiency is getting increased. If I double the length, the loss becomes half. If I triple the length, the loss becomes 1/3. I am gaining efficiency, but obviously there is a price. I am using double the steel and copper and magnets. Everything is becoming bigger. So, if I invest double in the cost of the material, then I am halving the losses. Again I get less current for the same torque, or for the same current I will get more torque, whichever way we want to view it, and the speed is lesser because the back EMF constant is higher. Is this fine? Now I will very quickly take you through a few slides before we wrap up. We have always talked of rare earth magnets because they are very strong, very powerful, but rare earths, as the name itself suggests, it is rare and therefore very expensive. And not only is it expensive, but its price tends to go up and down very often, and this is some graph of how the price went up and down. You can see that in a span of something like from 2010 to 2011, in a period of 1 year, the price went up from something like 25 to 450. So, nearly 20-fold increase or 25 times increase in price, very rapid, and then again it came down, again it will go up. So, it is not possible for you to plan properly if you do not know what the price tomorrow is going to be. It is one disadvantage, and what is even worse is that this is all the per kg cost. Compared to this, which is about 500 per kg at its peak, this thing is about 3500 per kg, and this dysprosium is a small additive that is put to improve the temperature rating of the magnet. So, both of these together is what makes for the rare earth magnet, and together they make it very expensive. So, what people have been wondering is, we already seen that PMSM motor has magnetic torque and reluctance torque. Can we increase the reluctance torque part and reduce the magnetic torque part so that we do not depend upon strong magnets? And this is possible. There is what is called a continuum, there is a range of designs possible. The normal surface permanent magnet motor has no reluctance torque. So, the reluctance torque is on this axis and the magnetic torque is on the x axis. It has fully magnetic torque and no reluctance torque. Then the PMSM motor, internal permanent magnet PMSM motor, has good amount of magnetic torque. It also has reasonable amount of reluctance torque, and then I can keep on changing the design in such a way that finally I use no magnets at all. This is the extreme. So, all the torque I get is only reluctance torque, there is no magnetic torque, and what you see here are some weak magnets mixed with reluctance torque. So, you get some magnetic torque and some reluctance torque. These are all ways of getting away from rare earth materials. This zone is where you will need rare earth magnets. Here you can use non-rare earth magnets, here you are using no magnets at all. So, this is the continuum of designs. This would be called a synchronous reluctance magnet, this would be called a permanent magnet assisted synchronous reluctance. This is the internal permanent magnet synchronous reluctance motor with rare earth magnets, and this is a surface permanent magnet motor. The challenge is, can a rare earth free motor, a motor without strong permanent magnets, can it deliver high efficiency, can it deliver high torque density? Torque density means how much torque do I have per unit volume. It is possible to make a very big motor which will deliver the same torque, but I want to do everything in a small space because otherwise I cannot put it on an electric vehicle. So, for a synchronous reluctance motor, the designs would be like this with no magnets, or you can have permanent magnet assisted ones. There is a close up view, you see that there is a lot of air gap. This is the D axis and this is the, so this is the D axis, this is the Q axis, and as you can see, the reluctance in this path is very high, full of air pockets and magnets, and the resistance in this reluctance in this path is very low because it is fully steel, and the difference between reluctance is what causes the reluctance torque. Then we have a different architecture called axial flux. We have seen motors where this is the rotor and around it is the stator, and the magnetic field is going like this. But we can change this architecture, and I can have an arrangement where the rotor is like this, there are permanent magnets here all over the surface, and the windings are on the left or on the right or on both sides, and the magnetic field is going like this. That is the kind of picture that you see there. So, all these this architecture is nice because the axial length of the motor can be very low, and I can make instead the diameter high, and one advantage of making the diameter high is that I can get a much higher torque, because whatever is the force multiplied by radius is the torque. So, I can get high torque with low RPM without using a gearbox in between, and there are a lot of challenges, particularly in the mechanical and thermal design, but when it does get to work, this is a typical example of axial flux motor. You can see that it is about 1 foot in diameter, but its axial length is only 3 inches, and I can get a very high torque of 115 Newton meter and go to a good speed of 2600 RPM, and I get 30 kilowatt, very high. So, the power density and torque density can be very high with this kind of a architecture. And finally, I will quickly walk you through a couple of interesting innovations that we have done in our lab, which I think will have great potential in the context of new evolving EV architectures. When the power of a motor or a controller becomes more than a certain threshold, then the losses also tend to increase, and when the loss increases the size does not increase in same proportion. When the size does not increase, the area available for removing the heat does not increase, but the heat increases. So, the heat flux becomes very high, and when the heat flux goes beyond a certain point, it is not possible for air to take away the heat. Then what do? You supply water, because water has a high specific heat. You make water circulate around the motor or the controller, and it will take away all the heat, but then that is not sustainable because the water will get hot. Again you have to remove heat from the water. How do you remove heat from the water? How do you remove heat from the water? Again you have to use air, because finally the only place where you can reject air heat is the air. So, with liquid cooling as they call it, the setup is a complete mess. It is like the tail wagging the dog. The cooling system is much more complicated than the thing that you are trying to cool. There are valves, there are hoses, there will be leakages, there have to be filters, you have to make sure there is no corrosion over time, a lot of things. There will be pumps, okay. So, the pump will require a motor. So, So, to cool a motor using another motor that is the kind of thing. So, we used what is called two phase heat transfer. I will not go into detail, but the reason why on a hot day we sweat and then when we sit under a fan we feel cool is because the sweat evaporates, and evaporation absorbs a lot of heat and then leaves our body feel cooler. This is two phase, liquid becomes vapor. So, whenever there is a transition from liquid state to vapor state, the removal of heat is very high. So, the something called a heat pipe is a hollow copper pipe, but it can conduct 100 times better than a solid copper rod if I have a few drops of water inside it. That is the construction of a heat pipe. This is just a cross section showing different constructions, and we have used that in designing a higher power, higher wattage motor, where some heat is removed by air in the normal way, but much of the heat which is beyond the capability of air to remove from here is conducted away by heat pipes. These are the heat pipes, and then there are many closely spaced fins at the other end of the heat pipe, and inside here what is not clearly visible is a radial fan, axial inlet, radial outlet, which will blow a strong gust of air and take everything away. So, whatever you are seeing here which is being done by the liquid and the hoses is being done by the heat pipe, and then finally what is colloquially called as radiator, which is a long network of pipes with fins through which a fan is blowing, that fan is kept over here. So, you do not have any leakages, there are no moving parts. Similarly, when we tried to work on the controller of a high powered motor, yes, the heat was higher. What made the job challenging is that the component generating heat is very small. It is just 4 inches by 2 inches, it is very small. So, the high heat, not only is the heat high, but the heat intensity or the heat flux is very high, and normally you have to have very complicatedly machined components with high pressure liquid to remove all the heat. We got rid of all of that by using something called a thermosiphon, and a thermosiphon is about 4 times better than a heat pipe. The only constraint being that the thermosiphon has to be vertical. Since our motor was being kept in a horizontal direction, we could not use a thermosiphon, we used a heat pipe, but the controller can be kept in any orientation, it does not matter. So, we chose a vertical orientation, thermosiphon, which is also another two phase cooling method in order to evacuate the heat economically without requiring all these liquid cooling systems. This is about all. Hope you enjoyed the course, and I hope that you will all build not only vehicles, but build the motors and controllers that go into your thing, because the optimum is more than the sum of the parts. If every component can be designed by you, then the net result is far superior to simply assembling individual parts. I can see that there is a rash of startups which are trying to build electric vehicles of different configurations, but almost all of them I see are just buying different components and assembling them. But what will really make a difference in the quality of what we build is when we are able to design every part according to a final requirement and align it, and that is what I hope you will be able to do. Thank you.